how it goes. So, okay. So welcome everyone to the third week, I believe, of the TAG seminar. Today we have Gustav Berth from Munich, and he'll be talking about Grothendieck Prestable categories. So Gustav, please take it away.
Thank you. So let's start. So the first thing, so for the first half, we'll talk a little bit about like tensor products of Grothendieck prestable categories. And we need one theorem for that, which we will not prove. Um, and if you at any point cannot read what I write, please interrupt me and I will try to write it again. So we will need like some kind of version of the Gabriel-Popescu theorem. So I will just call it Gabriel-Popescu. So if we have a category C, then the following are equivalent. So first of all, one is that C is Grothendieck prestable in Groth. And the second is that it's a localization of an of a modular category. So there is a in E1 algebras connective such that C is an accessible localization sorry, an accessible left exact localization uh, of R mod of connective right modules. And because I will be a little bit lazy, I think I will just not write the R. So I will just say modules. And you have to like remember we're talking about right modules, but I mean it doesn't really matter. Uh, so this is like a theorem, like it's proven in higher algebras and SAG in the appendix. Um, it's like true. And we will need this for the following reason. So we would want to try to construct a tensor product of Grothendieck prestable categories. And the problem is it's not clear that the tensor product of two Grothendieck prestable categories, the tensor product in PRL, say, is again Grothendieck prestable. So this is where we will use it. So this is the theorem that we're going to discuss now. So we have Groth, which is a subcategory of PRL add, the additive categories. I mean, connective half of a T structure, so it's additive. So this contains the monoidal unit, SPCN, and is closed under the tensor product. So PRL add, it just inherits the tensor product from PRL, and the unit is SPCN. And in particular, from this theorem here, from Grothendieck being closed under the tensor product SPCN, we get that Grothendieck is again symmetric monoidal. So uh, then Grothendieck is symmetric monoidal. Inherited from PRL. So, but the first thing, like, it's clear that SPCN is in Grothendieck in Groth. So the actual hard part is just showing that it's closed on the tensor product. And for this here, we will use this theorem, this Gabriel-Popescu theorem. So we'll just take two. And we choose connective and inclusions from C into and D into B modules. And so the study is just to exhibit as C tensor D as again some kind of localization of some module category. And okay, so I forgot to say this maybe. These guys here, of course, have lex adjoints. Um, so I will not do this in detail because this is kind of a little bit technical, but what one can show is one can show that if I look at if I look at this category here, A tensor B modules, this here is the same as um, this here is the same as uh, A modules tensor B modules. It's just kind of true. But the point is now from here, we get a functor through C tensor mod BCN simply by taking like the right adjoint of our inclusions and then like tensoring it with C. So the same thing we can do for D. So we have another map like this. We have these two maps, and these are again. Oh fuck. Uh, this is bad. I'm sorry. I misread my stuff. So what you kind of want to do, you want to do this in reverse, right? You want to take C tensor mod B and include it into here, and you want to do it in the other way, and then you want to show, okay, hey, these guys are both again fully faithful and admit legs left adjoints that legs functors exist like this. Maybe this is fixable. So the point is now that uh, and C tensor mod BCN in here. This is fully faithful. And similarly for D, I mean identically for D. And so the thing is now that one can actually compute one can compute that C tensor D is simply given as C tensor mod ACN intersected with D tensor mod, no, sorry, with this is all stupid. No, mod B. That this here is to say mod. One can compute that. This is like a relatively easy computation using like the formula for the tensor product in PRL. And then we still have an inclusion like this. We have an inclusion like this. And then one can use the fact that because the inclusion of this first component and the inclusion of the second component both admit legs left adjoints, um, right adjoints, that this here it still admits a legs right adjoint. So left adjoint. I'm so sorry. I will mix up these again. I'm so sorry. Yeah. So and this kind of computes the proof. This here is again that it still admits a left adjoint. It's still not trivial. Like you still have to argue somewhere there, but like this is just general nonsense. So this kind of concludes the proof for that. And hence we now have a symmetric monoidal structure on Groth, and the symmetric monoidal structure is just computed as you would compute it in PRL which is very nice. But now last time we saw a bunch of like definitions in PRL and we want to know how they interact with how they interact with the tensor product. And the proposition here, the relevant proposition here is following. So if f from C to D is a morphism in Groth, and E is also in Groth, then we have two things. One, f is Lex. This implies that so is f tensor the identity. And the second is that if f is compact, then f tensor the identity is also compact. And then these statements here, so the first one here somehow uh, the first one somehow uses uses Gabriel Popescu again. So I would like to, for time reasons, not discuss it. It's again like a very similar argument to here, where like you identify things on with module categories and then show that some functor between module categories is Lex or something. So this is kind of not super, not super, not super relevant for us, but the second one is maybe a little bit more fun. So I would like to like to prove it. So last time we had the following characterization. So that f from C to D is compact if and only if the right adjoint of the spectrification SPF preserves small colimits. I.e., because we're between presentable categories, it admits an adjoint. Um, so we use it then following, right? So we call the right adjoint of SPF, we just call let's call it G. So then G is again a morphism in PRL, and okay, because it's between stable categories, it's a morphism in PRL stable. So okay, what does this imply? Well, this implies that we can tensor with E, right? We can tensor with SPE. So then uh, G tensor the identity of E is still in PRL, and it is the right adjoint of this guy. But now we're in business because G tensor the identity of E being in PRL means it's in particular colimit preserving, or it's equivalent to being colimit preserving. So this means the right adjoint of this guy here is colimit preserving, and uh, hence by this observation above here, SPF tensor the identity is compact. And that's kind of nice. Um, and now we have something this is kind of nice, but now we want like more control over colimits. And there's a proposition I just don't want to prove because we also there's so it's true, but I just don't want to prove it. So we have C in Groth, and then we can consider the composite here to here to here, given by tensoring with C here. This preserves small colimits. And so this makes sense because last time we discussed that like Groth AC has colimits. So this is in fact a statement that makes sense. And I will just not prove it. Prove without proof. So I have not looked at the proof, but the proof should somehow there should be an analogous version for not almost compact things, but compact things, and the proof for that should just go through. So this is a kind of a very brief discussion maybe of some of the tensor product and how it interacted with notions from last time. And now we will introduce a new notion. So this is kind of maybe a little bit of it's like also a very natural notion, and the notion is called completeness. And it's kind of the idea is just to capture what a um, what a complete like the connective half of a complete um, T structure would look like. So we need a little bit of notation. So the notation we will fix is the following. So for an object C in Groth, we define C hat simply as the limit of, I mean, the obvious tower. So, and again here we're not really doing anything with the with the and this is really again like truncated in the topos sense, right? Because we're not in a T structure, so we kind of it doesn't really make sense to talk about truncated in that sense. But it doesn't really matter too much. But so now, of course, there is a canonical map. C to C hat. And this map is like kind of the goal is to show that this map kind of exhibits something as a localization. Um, but before we get there, we have to introduce the definition with what we're trying to localize. So if I have a guy here in Groth, it's called complete if the canonical map from C to C hat is an equivalence. And now what we do, we just say, okay, we give the category a name. So we write Groth comp for the full subcategory on the complete guys. Oops. On the complete guys. So now we have this morphism here, and we want to do the obvious thing. We want to show that this construction here, that this here exhibits Groth comp as a localization of Groth. And for this, I mean, we just prove that's a relatively lengthy proposition. Um, so this is following. So first of all, okay, surely the first thing we have to establish is that if I have some kind of C in Groth, that C hat is then also in Groth. The second thing is that okay, this morphism here is colimit preserving and left exact. And third, now the next thing actually makes sense. So oops. For every D in Groth comp, we now have a map from here to here. This map is well defined because we will argue in two that this morphism is colimit preserving. So that this map here is an equivalence. In other words, this just exactly says that Groth comp is a localization, right? And one is kind of one is kind of comparatively easy. So the idea is just that, okay, we want to exhibit C hat as the connective half, as the connective objects in an appropriate stable category with a T structure. Oh, I'm sorry, this should not happen with a T structure. And so I will just say this. So what you can just kind of do, you can do this construction from the first chapter of higher algebra, where you just like compute completions there and just take the completion of so I'm sorry. You first pick you first pick a you first pick a stable category where C is the connective half of a T structure on. And then you say, hey, we can complete it in the sense of like high algebra chapter 1.1 or something. And then we can say, hey, this shows, then you can show that C hat is the connective half of a T structure in that category, and then you're pretty much done. Maybe you have to argue like a couple of words uh, about the T structure being compatible with filtered colimits, but that's comparative. It's very easy. It's like mostly stuff from higher algebra. So and two is just kind of inspection of the proof of A. Proof of one. I'm so sorry. So the really interesting part, is, at least to me, is three. So okay, we will just first of all, now that we've shown two, we know this is column preserving between presentable categories by one. By one C hat is presentable, and so we can choose a right adjoint. So this is what we will start out doing. So choose a right adjoint or choose let something be the right one, maybe better. Um, let G from C hat to C be the right adjoint to, let's call the map F, canonical map from C to C hat. So by definition by definition, we also have the canonical map from D to its completion. So we have the canonical map from D to the limit of this tower. This here. And this is an equivalence. Because D is assumed to be complete. So now, what we now get, we get that this map that we're interested in and this is the limit of the maps here for where we just kind of restrict to the to the untruncated parts of D. So from C hat to like this. So this is now kind of nice. And now we will use the standard trick where we kind of identify that these here can equivalently be described by right adjoints. So now,
Shouldn't it go from dn to dn minus 1?
no, this is, I mean, we take the limit of this diagram. right? In arrows.
I
And we
see.
have,
Sorry. Thank you.
no worries. That's a good point. So we take the limit in arrows of the diagram of this sort, like this. Right? And the limit of that will just be the thing that we're interested in. So now, what we're trying to show that each of the individual maps is already an equivalence. Ah. And for this, we will use this usual trick. We say, okay, left adjoints are this category here of these guys are equivalent to like right adjoint functors. So what we can do, we can identify theta n with the morphism from here to here. And that's just this guy here, given by post-composition with G. And now this is kind of very nice for us because uh, G is uh, G is left exact because it's a right adjoint. G is left exact because it's a right adjoint. So um, what do you observe? You observe that by like this usual game about preserving pullbacks. You observe that G sends n truncated objects to n truncated objects as it's a right adjoint. So now what this gives us that this gives us that this thing here kind of decomposes. So it suffices to show uh, that if I take G and I restrict it to C hat less than or equal to n, this is now something from C hat less than or equal to n to C less than or equal to n, that this is an equivalence. But okay, uh, but this guy is right adjoint to F restricted to C less than or equal to n, which is an equivalence, right? And why is this an equivalence? This is just simply because you with an equivalence because C less than or equal to n is simply uh, C hat less than or equal to n. Right? This is like somehow again this is like in higher algebra chapter 1. So now we are done because now we know that G is an equivalence as we want, and this concludes the proof, which is really nice. So now we have some kind of now we have like we know that our notion of completeness is somehow good, and that it's a localization. And now and let's maybe write this down. So So now we have this notion, but now we want to investigate how it interacts with the tensor product, with the notions we already defined, so with left exactness and compactness, and also with the tensor product. And for the first thing, this is the content of the next proposition. So if f from C to D is a morphism in Grothendieck, in Groth, and f hat from C hat to to D hat is the induced functor, well, then we have two things. So f is Lex, then this implies that f hat is also Lex. And two, if f is almost compact, then f hat is almost compact. But in fact, the converse is also true, right? If f is almost compact, f is almost compact if and only if f hat is almost compact. And so the proof of this, so maybe the proof of, so the idea is somehow that as we kind of implicitly have seen here, the dimorphisms C to C hat and D to D hat, they restrict, and their right adjoints, they restrict to equivalences on n-truncated objects. So now it's maybe not super surprising that 2 is true, because this is just a notion that only dependent on almost compact heads. It's only dependent on the truncations. So this kind of immediately implies 2. This is immediate. And now for 1, this is very similar because here you just kind of use the completeness stuff. No, I'm sorry. And I'm sorry. So for 1, you just compute. This is a relatively immediate computation. So this is kind of very nice. And now we have kind of thought about one of the two questions, but the second question is about the tensor product still remains open. But before we talk about that, we have to fix a little bit more notation. This is unreadable. So we write this and for the white subcategories, on Lex, respectively, almost compact morphisms. And note that by the proposition, the second guy is still a localization. I should probably about the next line. Is still a localization. So now this is kind of, so now let's actually talk about tensor products again. So the first thing is that, oh, I'm sorry, we're not talking about tensor products again, we'll talk about limits and colimits. So this here admits small limits, which are preserved under inclusion into cat hat. And the second is that Groth AC comp admits small colimits, which are preserved under inclusion, and are not preserved under inclusion. They're preserved under inclusion into Groth com. I'm sorry. This is what I want to say. So last time we proved, or we discussed why Groth lex comp admits small limits, and they were not lex comp. Why Groth lex admits small limits, and they were preserved under inclusion into cat hat. And we discussed why Groth AC admits small colimits, which are only preserved under inclusion into Groth. And so this is just kind of the analogs of that, where we can only hope for inclusion into these two categories because it's just already wrong for the, or it's because it's wrong for the, if we drop the comp assumption here. So proof of one is somehow, I think I only wanted to do the proof of one. So uh, so we discussed last time that Groth lex admits small limits. And they are preserved under cat hat. So it suffices to show that the limit of complete uh, complete objects in Groth or in Groth next is again, but now this we're in business because the definition of where is the definition here? The definition of completeness was done via limit, right? And limits commute. So this is clear. As limits commute. So I didn't want to discuss the second part, but now what I want to discuss a little bit, I think my time management is a bit off today. I'm sorry. I thought I originally had way less time than I had, and I thought I would be way slower. So we will maybe come back to the first proposition after we're done with the main part. Because if we will still have a lot of time. So I'm sorry for that. But so we now have oops, I'm sorry. So without proof. So now we will actually discuss tensor products again as advertised. So the localization, I will call this functor hat from Groth to Groth comp. This is compatible with the symmetric monoidal structure. In particular, Groth comp inherits a tensor product. And we will call this tensor product by the usual tensor product with just a completion above. So this is like the usual thing we have to check. So suppose f from C to D is a morphism in Groth such that it's an equivalence on completion, such that f hat from C hat to D hat is an equivalence. So now what we're going to show, we're going to show that if we tensor with any other guy, we will still remain an equivalence after completion. So take E in Groth and show that fun LD tensor E to that this here, the canonical map from here to here, is an equivalence for all complete guys, X. So now this is kind of a very cheap trick. Because what we can do, we can just the map that we're thinking about, the map in question, can be identified by just adjoining over. So can be identified this guy. But now I can interpret this map, which is induced from post composition by the map like this. But now this is an equivalence as f hat is an equivalence. Right? So this is kind of a very, very, very cheap proof, but I think it's kind of smart. Um, so now, uh, so now we have this. We now have a tensor product on complete Grothendieck pre-stable categories. And now the question is, okay, how does this tensor product now interact with colimits? So because earlier we at some point here discussed something about colimits in the tensor product, and there's an analogous proposition here. So the proposition is the following. So if C is complete Grothendieck pre-stable, then this morphism here, this composite here, uh, here uh, preserves small colimits. So again, here we will just consider the following diagram. So we consider the diagram this diagram, and this commutes. And maybe you have to say, I have to say one word about this morphism here. This morphism just exists, and because earlier we argued that Groth comp AC here in here that this is again a localization. This was just a consequence of the statement about morphism being almost compact if and only if its completion is almost compact. So what does this buy us? So commutes. So now the vertical maps, these are all localization. And so what it suffices to prove, it suffices to prove the statement, the result for the upper composite. And because we have a formula for localization, for colimits and localization, and then this is just like it says what it implies. But now we've seen this earlier, so has been claimed earlier. So this is kind of a very nice result. This kind of gives us again that at least for almost compact morphisms, the tensor product behaves well with respect to colimits. And now I mentioned already that my time limit is kind of off today. I'm sorry. This was originally the plan, this was the main plan for today, but we still have so much time left over. So I would like to do something in a little bit more detail, which we skipped a lot of detail on earlier. And let's return right to the beginning. If there are any questions so far, please feel free to ask. But I would like to talk again about the proof of this here. So about the proof of this statement here, because what I argued somehow that that 2 is true, but we haven't really argued why 1 might be true. Why if I have a morphism in Groth and it's left exact, then if I tensor it, I'm again left exact. So, and the proof of that is kind of cool. And it again uses some of these Gabriel-Popescu ideas, and I thought maybe let's talk about this again. So let's try to remember the statement of this proposition, and let's prove it somewhere below. So addendum to the first proposition. So let's actually prove the first part. So the first step is the following. So what you want to use, Gabriel-Popescu to reduce to showing that you're the following. If f from C to D is in Groth and Lex, then for any connective E1 algebra, A the morphism F tensor Cn is still X. So this is just kind of just use the fact that I mean that E is like a localization of mod Cn for some A, and then that the adjoint there is Lex, and then that essentially proves this that you can reduce to this case. So now what you have in this case, one has an explicit description uh, of this morphism mod A Cn in Cn of this here. And in fact, it's equivalent to this is equivalent to the morphism from here here. So because somehow our Grothendieck Prestable category is always tensored over connective spectra, it makes sense to talk about A module objects in C and A module objects in D. And then what you can argue, when you can show that this here, that this tensor product here is equivalent to this construction. And similarly for the other side, this is like some result in high algebra. And this works like in extremely great generality, right? This like just kind of works. And now what you still have to this morphism and the diagram uh, and the diagram that you kind of might hope for.
Sorry, stupid question.
Yeah,
You wrote C tensor and then mod connective A, blah blah blah.
yeah.
What if you do C tensor and then mod A without the connective? Do you also like it seems so? How is this equivalent if you have the connective part? I would have imagined that you would drop the connective and then you would get something like this.
I think the reason is that so if you're if you are if you are if you're a Grothendieck pre-stable category, you just tensor it first over your first tensor uh, over connective spectra, right?
Yes.
Is there
Yeah, so tensoring by connective spectrum is the left adjoint, right, to the inclusion of
yeah.
pre-stable. Yeah.
No, I'm sorry. I mean that yeah. So I don't think are you tensored over spectra in general? Is your Grothendieck pre-stable category uh
No, I don't think so, right?
no,
I
right?
think only on the over connective, I think, yeah.
Yeah.
No, right. If you were tensored over spectra, you would be stable, I think.
Yeah.
Yes.
Yeah, that's right.
So I think this kind of boils the fact that this is true, I think boils down to the fact that you only tensored over connective spectra and not over spectra in general. I think this is where the point is where this goes in. I think I'm not I don't really understand I don't really understand categories tensored over something super well. So if somebody has a better explanation of this, then please feel free to chime in. But the statement here is somehow that this diagram still commutes. And now and we of course know how colimits are computed in what's the B doing there? In mod they are computed underline. So, I mean, after forgetting to here. So, but now, I mean, the bottom guy here is an equivalence, is left exact. So, limits and colimits and limits, colimits. So the bottom horizontal arrow is lex, and thus so is the upper one. So this is kind of the way you prove this result, and you really need this identification here. And earlier in the proof or in the proof idea maybe of the first statement we proved or discussed that. Let me just go there. Here, and in this statement here. No, and here. And in Grothendieck being closed under the tensor product in PRL add. I said something about that this year is, of course, not what I should have said, but what I wanted to say is somehow that these morphisms here are fully faithful and admit adjoints. And the way you prove this is again using a very similar formula. You use the same formula that you can write this guy here somehow as like this. And then you use some result about adjoints for module categories from higher algebra. So this is kind of like really integral to the entire discussion here that these things really can be identified with these module categories in this way. So this kind of underlies everything that we're doing here. So I think this kind of concludes what I planned for today. I'm sorry for the talk being so short. Are there questions?
Yeah, so let's thank our speaker first. And yeah, so we are open to questions. So there's also going to be like a post-recording session. If you don't want to ask your question here, then you can maybe ask it later. So we'll wait for like 10 more seconds.